Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
Thank you for coming. We have with us Dr. Lionel Briand from Carleton University. He's also a visiting professor at Simula labs in Norway. He's actually going to talk to us about building quantitative models for software engineering. He's previously been affiliated with the Fraunhofer Center for Experimental Software Engineering and with the Software Engineering Laboratory in Maryland.
Thank you. So first, I'd like to thank Nashi for inviting me here and organizing my trip. This is my first time here in Redmond, so I look forward to the next 3 days of discussions. So my objectives in this talk is to reflect on the last 20 years of research and practice in the field of software quality measurement, analysis, and modeling. So I'll try to provide my structured overview of what is a state of the art instead of practice. I'll use examples from my own work for convenience to illustrate guidelines and recommendations. And I'll try also to highlight the challenges that we face. And though there are no silver bullets, you will see that there are a number of practical, useful techniques that can help people control the quality of the software products. And I'll mention, a lot of the work I mentioned is actually joint work with a lot of people around the world. So I always like to start my talks by providing definitions of the key terms I'll be using. Measurement, this is a word I'll be using a lot. So the most general definition I can come up with is a logical rule for assigning numbers to observations to represent the quantity of a trait or an attribute processed. A model, I'll be talking about modeling very often, is a theoretical construct in the sense that it's an abstraction of reality that represents physical, biological, social processes with a set of variables and a set of logical and or quantitative relationships between them. And what we do in software quality engineering is that we try to measure and model software products and process attributes in some way. Yes?
Maybe better off not to define model. I think this definition is so general.
That's true.
So
but you
suppose
see,
I write a paper trying to prove the modeling of the... It's still theoretical construct that represents some kind of processes with variables and logical relations. And the very first use of modeling is empirical. So we get now empirical theoretical construct.
yes, because there are different models. Some of them are empirical, others are not. So that's why it's between parentheses. Yes, but well, we can discuss all the definitions of models if you want later on the slide. But so why do we, why do we measure and model in software engineering? Well, there are several reasons. One reason is to assess various quality attributes, such as reliability, testability, and maintainability. Another reason is to predict. We want to predict maintenance effort, for example, based on a number of properties of the software product itself, the changes that are taking place. We want to be able to quantify the impact of new technologies. So, for example, if you decide to use certain type of code assertions during testing, what will be the impact on the diagnosability of failures? That is the ease with which you'll be able to locate faults. And to do that requires the construction of models. So to assess product attributes such as reliability or testability, you need decision models. Because assessing implies that somehow you decide that you need to take an action on it, that you need to refactor your design, that you can deliver your software product or not. So you need some form of a decision model. Well, of course, predicting implies prediction models, usually in our field, statistical models. And when you want to quantify the impact of a technology, what you are basically doing is that you are building a causal model. You are saying, well, if I apply a given practice, I will get a 20% improvement with respect to debugging, whatever, under certain conditions. So we see that those are basically the three main type of applications of measurement and modeling in software engineering. And I'll give examples later on of such models. Models can take a variety of forms. And the reason is that they are used throughout natural and social and economic sciences and in most engineering disciplines. They can be mathematical functions and relations, such as in reliability growth models. They can be stochastic processes, for example, model using Markov chains. They can be rules of inference. For example, when we try to classify fault-prone components during software developments to focus verification. They can be fitness functions when we try to optimize something. For example, when we try to find an optimal integration orders to integrate classes into subsystems. And I'll get back to that in more detail. They can model cause-effect relations, like pair programming decreases fault density by 20%. You can use statistical techniques such as path analysis, for example, for that purpose. They can be simulation models. So, and all those are models that you can find in software engineering research. Of course, the main issue is to know what kind of models you need in order to address a given problem. So first, what are the issues in software engineering measurement? Main one is that many attributes are not easy to quantify. I mean, very often in object-oriented design, people talk about class cohesion, for example. But I don't know if you ever had a chance to look at measures for class cohesion, but they are at best questionable, because it's a very hard concept to quantify. In terms of external quality attributes, for example, design testability, very often people talk about testability. But have you ever tried to define what testability means? It's a very complex thing to define and quantify. And many other attributes are related to human perception, like the usability of a tool. So how do you quantify usability? I mean, it's pretty complex. Or another problem is that many of those attributes are multidimensional. For example, I'll give an example in a couple of minutes on testability. There are many factors that are involved in or that are contributing to testability. And so I'll get back to that in a minute. So what that implies is that measures are necessarily a simplification of reality. And as a result, the validity of a measure is context dependent, because you make simplifying assumptions in a given context to be able to measure a concept that is very complex to quantify. And as a result, of course, the validity of that particular measure is going to be necessarily limited to a very specific context. The specific development process and artifacts and application domains, And I'll get back to that issue in the remainder of the talk. So let's take an example, for example, testability. So it's a complex and fuzzy notion, as I said. At the most general level, the way you can define testability is to say that, well, testability is any factor that impacts the effort required for testing and its effectiveness. That's if you want to be as general as possible. But, of course, many different types of factors contribute to testability. The representation of your design and specification. Is it amenable to model-driven testing, for example? The implementation, such as coding standards, the use of assertions, contribute to testability. Built-in test capabilities, whether you have in your code building test capabilities for helping controllability and observability of your code. This contributes to testability. Your test suite effectiveness and efficiency. To which extent your test procedures are automated. And of course, what kind of systematic test strategies and criteria you apply. Okay? And all those things contribute to testability. And of course, what aspect of testability you are interested in depends on the context and the purpose of your measurement. because you are never going to have to address all this at once in a given context. So for example, we have a paper, and I have a list of references at the end of my slides on how to assess the testability of object-oriented designs. So we only focus on a subset of those aspects. And this is an example for testability, but almost any external quality attribute in software development is as complex as this one. So we see that at least at the top level that there are 6 dimensions to testability. So if I take a specific aspect of testability, which I call stubbing complexity. So in a typical object-oriented software, you have many dependencies and many cycles among classes. The problem is that when you try to devise an optimal integration order, for example, you try to integrate classes into a subsystem, and you want to minimize the stubbing effort, the effort required to stubs during testing, those cycles create a lot of problems, there is no obvious order. So you need some form of a decision model that tells you, well, this is a better integration order than the other. I'll get to it in a minute. It's a standard term to refer to a piece of code you need to develop in order to test another piece of code. So for example, if you have 3 classes, A depends on B, and you are basically, of course it's a trivial example, but you are basically integrating those 3 classes in that order, A, C, and B. Whenever you are testing A, you don't have B yet available. So you need somehow to emulate the behavior of B to be able to test A. Okay? And this problem occurs when you have cycles of dependencies. And the cycles of dependencies are very common, in object-oriented software. I mean, it's everywhere. I mean, you have thousands of cycles in there, typically. So what we wanted to do in that piece of work that I reference here was to provide an automated way for people to devise optimal integration orders. However, we needed some kind of surrogate measure for stubbing effort. That is, given a dependency in a dependency cycle between 2 classes, what would be the cost of stubbing that class while testing this one? So what we did is that we used coupling measures as surrogate cost measures. That is, the higher the coupling between those 2 classes, the more expensive the stubbing of B, because the more you depend on many features of B. Okay? Of course, it's a heuristic. So what we did is that based on dependency information and based on coupling measurement, we tried to devise an optimal integration order, assuming that this basically was a combinatorial optimization problem. And what we did is that we used genetic algorithms based on that information to generate feasible but optimal integration orders. And I don't have the time to go into details, but this was also we had to do optimization under constraints. Not every integration order was feasible, and that's typically the case in practice. So, but here you see that we are using coupling measures. We are making a big assumption here, is that stubbing effort is proportional to coupling. And of course, that's the type of things typically that you need to validate, but it shows you how you need to make assumptions that are context dependent. And there are many reasons why we made an assumption in the context of this study. I don't have the time to go into this, but and as what we have basically done here is that we built a decision model for people to help people make decisions. And we had to define a fitness function. The fitness function to optimize was basically to minimize the coupling involved in the stubs to be developed. So what's important, context assumptions and simplifying assumptions are unavoidable. But what is important is that they must be explicit. That's what is important. There are no universal measures and models. They must be selected based on purpose and context, like we did. You have noticed that in the previous example, we only looked at a very narrow aspect of testability. It's a very, very small piece of it, but that's what we needed in the context of our decision model. Okay? So contextual assumptions are necessary to select important dimensions of an attribute, for example, testability, to decide of proper ways to measure it, to choose proper modeling technique, and to ensure the validity of a measure or a model. Even in simple reliability growth models, they have to make such contextual assumptions. For example, they have to assume whether or not fault correction is taking place, that whether there is reliability growth or not. They have to assume whether or not, while making changes, people introduce new faults, and that fault, and whether that fault introduction process cannot be neglected. And that affects which reliability growth model you will be using. But let me take another example from one of our former studies. We had a study on the impact of contract-based assertions on code diagnosability. So why? You know that in object-oriented software, a given functionality is spread across many methods. I mean, you cannot locate functionality in the code. Functionality is a result of a large number of methods interacting. So one of the difficulties is that people can spend, I'm sure you know about that, they can spend a great deal of time when they observe a failure to locate where the related faults are. And it's very time consuming. And if we use that diagram to illustrate my point, and if each path here is an execution path, this denotes the location of the fault, and this where the failure is detected. Then what happens is that in a typical context, you execute a faulty path, then you compare expected outputs with actual outputs, and you decide whether or not there is a failure. The problem is that there is a pretty long distance to go from the erroneous output to where the fault is located, and you don't have much guidance. So if, for example, you assume that you are going to use contract-based assertions to help the isolation of faults, then what happens is that if each interval here represents the execution of a method, at the entry of a method you check the precondition and class invariant, for example. At the exit of the method you check the postcondition and class invariant again, and if there is any violation, then you know that a violation took place at the entry or exit of a given method. And chances are that you'll be much closer to where the fault is located. But the point is that cost effective? I mean, is that worth it? Because of course there is a significant overhead entailed by using such contract-based assertions. First you need to define the contracts, and then you need to instrument the assertions. So we performed a study on a system, but one problem we had is that we had to quantify diagnosability. So we had again a measurement problem. How do you quantify this? What I'm going to do is I'm not going to define formally the concept of diagnosability here. I'm going to explain it through an example. So I'm going to use UML sequence diagrams to define that. So imagine you have an object on which is executing a method E. A message E is received and there is an execution. So at entry, as I said, we check precondition and invariant. At the exit, we check the postcondition and invariant, and we may have also additional data-related assertions being checked while executing it. So this is a simplistic sequence diagram. So you have a number of messages, a number of objects involved. Those are method executions on receipt of messages. So here we have the execution of E that I was mentioning here. Let's assume that an exception is being raised while executing E. And let's assume that the faulty statement is here, somewhere in the execution of C. Okay? So depending on where the exception is raised, we can count in a different way the methods that will require to be analyzed in order to find the fault. And this is how we are going to measure diagnosability. Diagnosability is going to be a distance measure that is going to be to try to assess the number of methods to be verified, to at least to have a chance to find the related fault, the fault related to a given failure. So if an exception is raised at the entry of E, then and I'll explain that in a minute, we assume that, well, the developer will have to check A, B, and C before finally encountering the faulty statement or part of C. If the exception is raised during the execution of E but before the call to F, then the developer will have to analyze a part of E, then A, B, and C before eventually finding the faulty statement. If the exception is raised during the execution of E but after the call to F, then typically one would try to look at the execution of E that was covered, then the execution of F that took place, then A, B, and C until the fault is found. So you can see here that we have inherently made a number of assumptions. We have a model of how people are going to debug the code, what they are going to check and in which order. We make an assumption about that. And this is a typical example of a contextual assumption that is required in order to be able to quantify diagnosability. Because the way we're going to measure diagnosability is to count the number of methods that we need to be analyzed. So of course this is driven by what assumptions, what contextual assumptions you make in terms of how people debug, what they will look at first. But of course the underlying assumption here may not be valid in another context. It depends on the tools and the practices. But it's necessary, otherwise there is no way to quantify diagnosability. And if there is no way to quantify diagnosability, there is no way to assess the impact of using contract-based assertions on the difficulty of locating faults. So in that study, just for the sake of providing example results, here is diagnosability on the y-axis. Here are simply the faults that we had seeded, ordered by their diagnosability when using a typical oracle, an oracle that simply compares expected outputs and actual outputs, a typical test oracle. So this is a blue curve. And the green observations here are basically the corresponding diagnosability values when using contract-based assertions. And of course, as you can see, in most cases, an exception is raised in the method where the fault is located. That is, diagnosability is 1. Okay? And there are, of course, a few exceptions. So based on such results, then you may decide whether or not the overhead associated with devising contracts and instrumenting contract-based assertions is worth it. Because here you have an idea of what the impact is going to be. Yes?
Was it just for reliability or was it functional correctness? So that no exceptions are thrown or that actually the sorting does so? So that's a different thing, right?
Here?
So partial specs or total specs.
Yes, here the contracts were functional contracts. Okay, we're not checking things related to performance or memory usage or, they were functional contracts.
Yeah, but actually the partial correctness, so only guaranteeing that actually things, that no exceptions are thrown, or that it's actually the correct behavior as expressed in the specification?
No, we checked whether it was a correct behavior. However, there is more to it. I don't have the time to go into all details. I'm providing an overview. But we checked whether the contracts needed to be complete. So what we did is that we checked contracts at different levels of details. And what we found is that even with very rough contracts, you get nearly the same results. And there are many other things. For example, we checked that whether or not those assertions could replace oracles, because oracles are very expensive to code. So we did a lot of more. We tried to investigate much more questions in that study, actually. So now let's turn our attention to modeling, not measurement, but modeling. What are the issues? Well, the issues depend on the type of model. If you are dealing with a causal model, you're trying to demonstrate that code assertions, help diagnosability. The problem is that you can never prove, of course, causality. In a typical environment, if you are collecting data on projects, you can never prove causality because there are so many factors that are confounded that could explain the result that you can just come up with your best guess. That's all you can do. And of course, you can always perform controlled experiments like they do in medicine, but it's rarely doable, in an industrial context. So it's not an option often. So you can only rely on some form of correlational evidence, and you need to have very strong theory. You need to really understand why you obtain the result you obtain. I mean, quantitative data are not enough, and you need to do some form of qualitative analysis to understand why you obtain the results you observe. But I don't have time to go into that level of detail right now, but we can discuss it later on. Another type of models, of course, is related to assessment, as I've mentioned before. The problem is that when you assess something, maintainability, whatever, external quality attribute, you always want to assess it relative to some form of a benchmark. Otherwise, how do you know whether it's good enough, not good enough? No, you have to have some kind of a baseline of comparison. And it's not easy to come up with benchmarks which would represent a baseline of comparison. So what people typically do is that they use past projects to build baselines of comparison. So they always compare what happens in the current project compared to what happened in the last 20 or 10 projects. But the problem is that not all projects are comparable. And technology is evolving. So that's often an important issue related to building assessment models. Decision making. So usually in decision making involves coming up with a fitness or evaluation function and optimizing it. But usually that fitness function is multi-criteria. You try to optimize several criteria at the same time. So you end up having to use optimization techniques that are complicated. And that's why in software engineering, more and more people turn their attention to evolutionary techniques, because they are more flexible and easier to handle when you really you are dealing with multi-criteria problems. An example was what I've mentioned before, in terms of devising optimal integration orders. So in our case, we had multiple coupling measures, not just one, measuring different aspects of coupling. So it was a multi-criteria optimization problem. And of course, prediction models, which of course are necessary for management purposes and other purposes as well. The problem typically with prediction models is that you have many explanatory variables. There are many variables that can possibly contribute to what you're trying to predict. Just imagine, trying to predict the correction effort after you release a product, or trying to predict where faults are going to occur in a given product after release. You can of course consider structural properties of your software, but you have to consider the change properties, what changes are taking place where, what type of changes. You have to consider human factors. You have to consider many other aspects. And all those, not only you have many explanatory variables, but they interact with each other in terms of determining what's going to be the release correction effort, for example. And the relationships between all of those variables is very complex typically. Those are not like always simple linear relationships. Many things are non-linear typically. So, the question is how do you build such models? It's not that simple. We don't have very strong theories to rely on in software engineering. So we cannot be strongly guided by theory. So that's another issue. So let me again give an example. It's what I do. It's what I do in that talk. I alternate general comments and examples that are based on real studies. So this is a case study that took place in a large telecom company, and what they wanted to do is in fact, they wanted to address a typical problem. Is that they had a legacy system, and each time they had a new release, they wanted to be able to focus verification on part that would be more likely to contain faults, the typical faultness prediction problem. So they would perform changes in a release, get feedback from the prediction model in terms of what were the fault-prone components, and try to focus V&V on this, to use more stringent test and inspection criteria on those components, if you will. And so you have the release cycle, and you have the more general corporate learning cycle, where after each release, you record the new release change in fault data, you update your fault prediction models, you package it in a tool with some kind of visualization mechanism. For example, we use tree maps to, because you can imagine a system as a hierarchy of components, and we use tree maps to help them visualize the likelihood of faults. And then people are deployed, and the new version of the tool is basically deployed, and people are trained. and etc. So you have a corporate learning cycle and you have a release cycle. But of course the question is how to build such prediction model in a legacy system context. Fault probability is a function of many factors. So this is an example of what I was saying before, that we deal with a large number of potential explanatory variables. The amount of change performed on classes, the size and complexity and coupling of the classes, the use of inheritance, the code quality in terms of code standards violations, duplication of code, human factors, of course the familiarity with the code in a given subsystem, and many other factors that we probably don't know anything about, that we try to capture using fault history. That's how we try to capture what we don't know. And so we tried, in that particular case, to use all those variables somehow. So we use typical model construction techniques. Here in that case, logistic regression. Why? Because we were trying to predict the probability of a class to contain a fault. So that was an adequate technique to use. We did all kinds of tweaking to the variables for reasons that I won't mention now, because there are a lot of practical issues that arise when building such models, like outliers, non-linearities, etc., interactions. So we had to deal with all that. And we wanted to perform a realistic assessment of that prediction model. And I'll get back to that in a minute. So what we did is that we tried to predict faults in version n of the system, using a model that was fitted on version n-1. And we did that on several versions. So what that means in that case is that you analyze the code of n-1 to collect a number of code metrics, I guess, and you use data about changes and fault corrections over the two previous versions. That's how we did it. And some data about the class history. When was the class introduced, in which version, how many faults happened, during the history of development in that particular class, etc. So the first thing to do is that we did a cross-validation to look at two specific evaluation criteria. On the y-axis, on the x-axis here, you have the cutoff probability value. We have a model that provides you with a probability value. Now, based on that probability value, you have to decide whether the component is fault-prone or not. So you have to use a threshold, a decision threshold. So here we vary the threshold. Then we look at so-called false positives. That is, what was the percentage of classes that were predicted as fault-prone, but that did not contain any fault. And then, of course, we looked at fault negatives, which is the other side of the picture, which basically is a percentage of classes that were predicted as not fault-prone, but that eventually contained a fault. And of course, those two evaluation criteria vary depending on the cutoff value. But if you use a somehow balanced cutoff value, you'll see that that number is below 20% here, when using version n-1 to predict version n. But that's not enough. One problem with prediction models that I haven't mentioned yet is that you need to evaluate their cost effectiveness. It's not enough to look at their accuracy. The accuracy doesn't tell you much about cost effectiveness. And how do you do that? Well, there are many ways, but let me take an example. So this is our probability cutoff value, okay? And we have a number of curves here on the y-axis. The first one here is the percentage of faults contained in classes that have been predicted as fault-prone. Okay? So you see that that curve varies around 75% roughly, depending on the cutoff value. Then, of course, what first thing you can do is you can say, well, what is the percentage of classes that are considered to be fault-prone? I mean, that will give you an idea of how much verification effort you have to spend as a result of using the model. So this is a curve for the percentage of classes. And you might say, well, it's pretty good. I mean, there is a pretty large difference in percentage between the percentage of faults I find in classes being predicted as fault-prone and the percentage of classes represented by those fault-prone classes. However, it's not that simple, because those classes tend also to be the most complex and the largest classes. So depending on the testing technique or inspection technique you use, this may not be really proportional to the increasing cost that is going to result from using that prediction model. So what you may want to look at, depending on the testing and inspection technique used, is a number of functions, or they call that functions, but number of methods, psychometric complexity, etc. And in that case, here are the curves that are more representative of the size and complexity of those 4 prong classes. And you can see that there is a significant difference with the percentage of classes. And so then you can say, well, one practical way of assessing the cost effectiveness of such a prediction model is to look at what I called the cost effectiveness area between those curves. This is what gives you, it's a way to quantify the benefits for a given cutoff value of using such a prediction model. So one issue with prediction models is not just to limit yourself to accuracy, no matter how realistic it is. You have to look at cost effectiveness. And the way you quantify cost effectiveness varies depending on the purpose of the prediction model. This is just an example. Anyway, another example. You know that very common techniques for testing, at least testing in the small, are white box testing techniques, where people use control and data flow criteria. And those have been used and proposed many years ago. But what's interesting is that we know next to nothing about their cost effectiveness. We don't know whether those data flow criteria have any use and they bring any advantage, even 20 years after they were proposed. And so here, this example is a study where that's exactly what we're trying to do. See what was the benefit of using such control and data flow criteria. And for the sake of facilitating the statistical analysis, we seeded a large number of faults. We also showed that those faults were representative of actual faults, but I'm not going to go into those details. And basically what we did is that we built some kind of a simulation procedure to automatically generate a large number of test suites that would cover 4 control and data flow criteria: block, decision or edge, CUs and PUs. And for each level of coverage for those 4 criteria, we generated a large number of test suites. And since we were trying to evaluate those strategies, we needed some kind of a baseline of comparison, again, because otherwise how do you know whether it's good or not, whether it's useful or not? And what we did is that we compared it with random test suites. And why? Because generating random test suites is nearly free, while generating those white box coverage criteria is extremely expensive in terms of code analysis, and it's not fully automated. So this seemed like a reasonable baseline of comparison to use. So for example, one first result, here we are looking at the relationship between fault detection and coverage, or coverage level. And the first thing you can see, of course, is that as expected, block for a given coverage level is less effective at detecting faults than, say, decision coverage or PUs. I mean, that's to be expected, since decision coverage, for example, subsumes block coverage. So but that's not very interesting. What's more interesting is that the relationship here is at best linear, and in the worst cases is mildly exponential. What that means is that even in the last 10 to 20% range of the coverage level, you still detect a lot of faults. There is no plateau effect. That means if you really want to be effective, you need to go all the way to 100%. By the way, this is 100% of fusible coverage, okay? Because you always have non-reachable code. So that was a result of one result of our case study. Another result looked at the relationship between coverage level and test suite size. The assumption here, and we can of course discuss it at length, is that the size of test suites was somehow proportional to the cost of testing. And of course, that's not really true when you try to compare test techniques, but that's something else to discuss. So what we noticed here is that as you try to achieve higher levels of coverage, it becomes more and more expensive. And really more expensive, exponentially more expensive. And as usual, you have the usual relationship between the different criteria. It's of course cheaper to achieve a certain level of coverage for block than it is for decision coverage, for example. Okay? Now, if we try to perform some kind of cost-benefit analysis and we compare those coverage criteria in terms to random testing, so one way to look at cost effectiveness is basically to plot fault detection versus size. That is, fault detection can be a measure of the benefit of using a given test strategy, and size, as I've said before, can be a surrogate measure for cost with a few caveats, though. And we can see that, yes, there is a difference, but the question is but that difference is more significant in the larger size range. That is, when you achieve larger levels of coverage. And the question is whether that difference is worth the additional overhead. And whether it's worth the additional overhead depends on context. It depends on the criticality of the software. It depends on many other aspects, on how much you have managed to automate your data flow and control flow coverage procedures. But you see that it's not obvious that this would be, that type of percentage would be worth it in any context, in any situation. So, and all the results I've been presenting here in the last 3 graphs are extremely important from a practical standpoint. If you want to use such coverage criteria, you need such data to make decisions. But that type of data doesn't exist. I mean, it's almost non-existent. And when there exist studies, usually they are not very well done from an analysis point of view. Anyway. Now, we talk about modeling, but in fact there is a huge number of possible modeling techniques that can be used that come from many different fields. And this, of course, comes in part from the fact that models are used for a variety of purposes. So, from, of course, a limitless number of statistical techniques to machine learning, to evolutionary algorithms, simulation procedures, simple Monte Carlo or system dynamics, Bayesian neural networks, and then techniques to help multi-criteria decision making, such as the analytical hierarchical process, or techniques to perform exploratory data analysis and uncover the shape of relationships and interactions, such as multiple adaptive regression splines, and many others that I'm not mentioning here. So, though there are challenges, there is a large number of techniques that are available to us to solve the problems, the modeling problems I've mentioned before. Of course, the difficulty is to select the right technique for the right problem. And this depends, of course, on the purpose of your modeling, classification, continuous prediction, decision-making, optimization. It depends on the type of variables you have, the number of variables, the type of variables, whether they're discrete, for example, whether you expect interactions between those variables, the form of the relationships between those variables, the amount of data you have available, etc. And there are many other parameters, selection parameters. And those techniques come from very different fields, and they require very different expertise. And that's the difficulty, that you have to be aware of all that, to know what's appropriate. So here is an example, another example. This was a study we performed in a Siemens business unit working on mobile telecommunication. And what those people were extensively using inspections in their analysis documents, their design documents, and some of their code as well. Code was combined with some form of unit testing, because they were using both inspections and unit testing. And the investment was so large in inspections that they wanted to know whether there was an economic impact, some form of benefit, and it wasn't obvious because the investment was very large. And a number of people who perceived inspection as burdensome, and they were questioning whether or not they were really useful. And there was also a motivation problem. Try to convince people to adopt a practice if they have no evidence that this is worth it. What we did is that we devised a practical method to assess cost effectiveness. But this involved a lot of things. It involved modeling cost effectiveness in a realistic manner. It's not that simple to come up with economic models that make sense. We had then to see how this could be implemented using both, you will see why, project data collection, I mean collecting projects, data on projects, but also expert estimates, you will see why in a minute. And then we use Monte Carlo simulation in the end to assess cost effectiveness and account for the uncertainty in that assessment. So the first step was to define a cost effectiveness model. And again, if you want to see the details, there is a reference at the end of the slides. But at a high level, what that cost effectiveness model was trying to capture was a ratio between the cost saved by inspectors minus the cost consumed, normalized by the potential defect that would have occurred without the inspections. The potential defect cost, that would have occurred without the inspections. You have to normalize it somehow, to make it meaningful. However, we realized very quickly that we couldn't collect the right data to implement such a model. I mean, the type of data that it would require would be impossible to collect. So it's nice to have a realistic economic model of cost effectiveness, but on the other hand, if you cannot actually use it because you cannot possibly collect the data that it requires to fit it, there is no point. So what we did is that we combined project data and things we could, for example, for design inspections, we could of course collect things like the total number of defects in design inspections on various projects and various inspections, with expert data, things we could not possibly collect through project data collection. And for that, we use expert elicitation techniques that came from other fields, in the social sciences, and for also techniques that were used in nuclear engineering to build risk models, for example. And we combined expert data and project data in order to estimate model parameters. And then we use the model to perform Monte Carlo simulation and obtain probability distributions of cost effectiveness, for example, in terms of proportion of rework effort saved. And we did that for code inspection, design inspections, and analysis inspections. So the first thing we found was something that we expected, but it was good to see it. Well, at least it's something that is widely expected among people who perform inspections, is that the earlier you perform an inspection, the higher the benefits. So here you can see that the distribution for analysis inspection is markedly higher than for design inspections, and same thing for design inspections versus code inspections. A second result was that we were not sure whether code inspections were really worth it, because you see, I mean, we are not very far from the zero value here, where there is no benefit, So then we questioned whether the code inspections, as they were practiced, were useful. And so we investigated and we found out that maybe one reason they were not very useful is that they were redundant with unit testing, and that somehow you needed to devise your unit testing and inspection procedures so that they would look for different types of faults and they would focus on different problems, which was not the case here. And then, of course, what was very useful is that we could definitely tell people that at least design and analysis inspection were really worth it, that they were bringing a lot of benefits, that they were a good practice. Now, of course, the question you may ask, and that's a typical difficulty when you come up with such assessment models, how do you know the model represents reality? I mean, we don't know the actual cost effectiveness. That's why we model it. So how do you know it? It has anything to do with reality. And I don't have much time here to discuss about that, but in the paper that is also referenced on the last slide, you have to use many indirect ways of validating your model. For example, the fact that we have that ordering between analysis, design, and code inspection is reassuring in a way. It tells us that, well, at least with that respect, the model seems to make sense. And there are many other indirect ways you can try to validate your model. But you will never find a direct way of validating such a model, because what you are modeling is unknown and cannot be quantified. However, you have an explicit model that makes explicit assumptions that can be questioned and that can be improved. This is not a black box. Well, what I'll do is I'll skip that slide because it's already almost 11:30. I'll get back to it if I need to. It's about 1 hour, roughly.
We have an hour and a half.
Yeah, okay. Okay. Another thing we did, quickly then, in the same context, is that we use MOS, which is a data mining technique, or should I say, an exploratory data analysis techniques, that tries to fit data in multiple dimensions in terms of splines, regression splines, and tries to also uncover interaction between variables. And so we use that in order to predict the number of defects found by inspections, depending on a number of inspection factors. Some of them being very simple, like the effort in terms of man hours invested in inspections, the number of participants in inspections. And when we found that there were many interactions that we didn't know about between all those factors. And so, for example, for a given effort value, if you increase the number of participants, at least within a range, you increase pretty sharply the number of defects you find. And this is a 3D surface area that models the relationship between effort, participants, and the number of defects found on the y-axis. And so such models can then be used to make decisions, or at least plan your inspections. You say, well, here's how many people I can actually involve, here's how much effort I can invest, what should be the number of participants, and you can decide of something that looks optimal based on such relationships. And of course, predicting defects is also useful because then you can plan for correction effort as well. So we did that in the same environment as the previous study. We built such prediction models. And they involved a large, here I only show 2 simple variables, but actually they involve a large number of variables. Because again, what contributes to the detection of defects in inspections, you can imagine a large number of possible variables to consider. But the reason why we use MOS, that exploratory technique, is that we had no idea about the relationships and the interactions that were taking place. We had no theory. How could we know that? And there were so many variables. So, and of course, we expected, as you can tell here, the relationships not to be linear. So, if I try now to summarize one important aspect of software quality, measurement and modeling, which is analyzing defect data. This is a large subset of the type of studies that are taking place, though that's not the only one. What people try to typically do is to predict faults or fault density, perhaps across category, like severity categories, correction effort, where faults are located, and reliability. They try to assess and compare defect density or defects to some kind of a benchmark. How the benchmark is defined varies. And summarizing roughly what you see around. Source and detection activities of defects. Like what is the defect slippage from one phase to the other? How many defects do not get detected and should be detected? Root cause analysis, why do defects get introduced? So those are typical type of analysis you find around. Of course, an important also category is to determine cause-effect relationship between verification activities and faults, reliability, rework. We want to understand those relationships because for the sake of process improvement, we need to understand that. But regardless of the type of problem you are trying to solve, you will never find common, universally applicable solution. So when you change context, the way you actually solve those problems changes most of the time. You have to come up with different measurement. Often you have to use different modeling techniques. And so it's a reflection process. It's not like you can read about a technique in a paper and then just apply it in a straightforward way in your environment. And that's what's difficult about it. So those are funny quotes that I got from a website, from a conference in a completely different domain that has nothing to do with software engineering. So models are at best are flawed maps of an uncertain terrain, abstraction of reality. You have to make sure that models are calibrated properly. They have a calibration problem. They also have difficulties to find what are the right variables, or how to find the best model that is the most representative of reality. And they also wonder, how do they know that if a model is wrong? Like the cost effectiveness model I've shown before. How can you determine that? And so they have a lot of the same problems we have. And this comes from a completely different application domain, which in fact is how do you model investments, financial investments? How do you optimize financial investments? So also they have to use optimization models, they have to predict, etc., etc. And they have exactly the same problems. So it's not specific to software engineering. But the solutions to those problems might be specific, in the sense that we don't work within the same constraints. So, at a high level, to conclude on a more philosophical note, models are mostly useful to structure the debate. They are not trying to capture a definite truth, a definite and permanent truth about something. It's a way for people within an organization to debate about things like testability, etc. It's a way to make informed decisions. And another way to put it is that it's an argumentative framework for applying logic and mathematics that can be independently evaluated by different people and can be applied in a large range of situations for reasoning, decision making. And it can be applied by people who do not necessarily have the expertise of the people who have built the model. So models are also reusable forms of expertise or reusable tools. Okay? And in all domains, not only in software engineering, they lead to hotly contested debates. But that's the nature of a model. It's meant to be questioned. It's meant to evolve over time. So, there is nothing wrong with that. So lessons learned from a more general standpoint. Measuring and modeling is not just a mathematical exercise. You have to understand the context in which you are applying measurement and models. You have to make context and simplifying assumptions. And you have to make the right ones. So there is something that goes much beyond the technical aspects of modeling here. Measures and models must be clearly and explicitly justified based on the process and product information in context. You need to clearly say, here are my assumptions, here's why I'm making those assumptions in that context. The validity and usability of a measure model varies with context, but also changes over time. In a given organization, in a given business unit, your models will have to change over time because technology changes. An assumption that was acceptable 3 years ago is not acceptable anymore. So you have to expect models to evolve and change. Your measurement to evolve and change over time. And of course, measures must be defined to be useful in terms of specific objectives. As I've mentioned before, most external quality attributes, such as maintainability, testability, are very complex. And you cannot usually measure and investigate all aspects of those quality attributes. So you must be driven by your objective. And usually this helps simplifying the problem to a large extent. However, despite all the challenges, there is a wide range of techniques. I've mentioned some of them, but there are many others. And so we can still, despite those challenges, if we are careful, we can still help people a great deal in terms of building assessment models, decision models, prediction models, in terms of quantifying the impact of new technology, etc. So I've tried to give you a realistic assessment of the state of the art and state of practice. I've tried to give you a realistic assessment of what the challenges are, but I don't want to imply by any means that those challenges are an obstacle to applying any technique to help people control quality. There is a growing practice and community in terms of the quality measurement and modeling. I mean, definitely over the last 10 to 20 years. People worry much more about it than they used to. Much progress has been made in the last 20 years in terms of the quality of research, the body of knowledge. From an engineering standpoint, there are many useful techniques that are readily applicable. From a scientific standpoint, it's a little bit more difficult. One difficulty we face is to generalize, to come up with general theories. You collect data in an environment, you find a result. You collect data in another environment, in 5, 10 other environments. And usually you get pretty different pictures. And then, how can you somehow, based on all that data, devise a meaningful theory? In other fields, that's what people tend to. They try to build theories, But in our case, it's still pretty difficult. But from an engineering standpoint, we can do a lot. Another problem, of course, that in practice, in business units, most people have computer science degrees, and they are still mostly ignorant of what you need to know to use such measurement and models. So there is an education problem that is a practical issue you have to address. And we are not fully comparable to any other engineering and scientific discipline. We can reuse from them a lot of the techniques, but it always requires some level of tailoring and adaptation. I mean, we can't just reuse a ready-to-use technique from somewhere else. We need to devise our own methodologies and standards, basically, in software engineering measurement and modeling. So there are a number of selected references which I've mentioned in that talk. There are many other examples and many other pieces of work that I haven't had a chance to mention. But I'll be here in the next 3 days and discuss with a number of people, so we can discuss other aspects of software quality as well. And if you have questions, we have time for that. Oh, thank you.
We'll continue our conversations.
Okay.
Thank you very much.
Thank you.